Good afternoon. My name is Don Ford, and I'm the Senior Manager, Hydrogeology and Source Water Protection at the Toronto and Region Conservation Authority. My talk today is going to be on the low temperature geothermal solution we're working on for our new head office location in North York, Ontario. My talk today will start with a review of the various technologies for low temperature geothermal energy, as well as some of the considerations that go into choosing which technology is best for your particular application. Then I'll go into a little bit about our site at 5 Shoreham Drive in Toronto, the field program we undertook, some of the lessons learned along the way, and our next steps. And at the end, we'll have some time hopefully for questions. So, what is low temperature geothermal energy? First of all, I'll tell you what it's not. It's not the high temperature situation you see with geysers in, say, Yellowstone or Iceland or New Zealand. Instead, it uses the relative thermal stability of the subsurface to provide energy efficient heating and cooling of buildings. And this can happen anywhere in the world. This technology, or these technologies, typically reduce the consumption of hydrocarbons in both heating and cooling systems. There are two main types, one being open loop, which typically has fewer holes, shallower holes, but wells. Those holes have to be completed as wells, which usually involve a permit to take water. On the other hand, there are closed loop systems, which are much more prevalent in Ontario, that typically have more holes and deeper holes, but no wells. So there's no water use or permit to take water required. Well, you may wonder how geothermal systems work and how they both heat and cool buildings. Let's take a look at a closed loop geothermal system in both cooling and heating mode. In cooling mode, it draws cool fluid from the subsurface, puts it through a heat exchanger, and what happens, the fluid on the other side of the heat exchanger is warmed up. That warm fluid is then circulated into the subsurface to cool down and be recirculated back up. In the winter, it operates in reverse. It pulls relatively warm fluid out of the subsurface, puts it through the heat exchanger, which cools down the fluid, and puts that cold fluid back into the ground where it warms up. And all this has to do with the fact that the ground temperature is a relatively stable 10 to 12 degrees, let's say in Ontario, and the air temperature varies quite widely from, say, 30 degrees in the summer to, say, minus 10 or 15 in the winter. So our site here, 5 Shoreham Drive, it's where our head office used to be and will be in the relatively near future. You can see it here. It still has the existing building in this Google image. It's located just southeast of the intersection of Jane and Steeles and just south of Black Creek Pioneer Village. Now we know that there's a major channel aquifer, a bedrock valley, going through this general area, but we weren't sure exactly where this valley was located. We had initially thought that this valley might be to the west, and therefore bedrock would be relatively close to surface, and a closed loop system would be more efficient and more economically feasible. With any geothermal system, you need to understand the building you're trying to heat and cool. In this case, the new TRCA head office is proposed to be a 4-story mass timber structure, as shown in this picture here. The heating and cooling profiles vary depending on the building size, footprint, number of stories, and the type of use. All these need to be factored in before choosing your particular solution. So in terms of our field work, the initial borehole was assuming a closed loop system and was drilled in January of 2019 using a mud rotary system. And what we found was a total overburden depth of 119 meters, so deeper than we were expecting. And and a total borehole depth of 198 meters. So, as I indicated, very deep. Now we found three possible aquifers. We found one here, right above bedrock, another one in about 50 to 70 feet below grade, and more sand and gravel above that. And therefore we thought with three possible aquifers that an aquifer-based system might be more feasible in this location. The reason is we'd need fewer holes with wells, or perhaps we could do it with as few as 2 wells. Based on that initial borehole, TRCA elected to drill a detailed continuous core hole using PQ core down to the bedrock surface at about 125 meters. And what this detailed core hole revealed was much more complex stratigraphy. Now you can see this is in meters in this case in this borehole, but you can see instead of a uniform sand and gravel, we have a much more complex interbedding of our clays, sand, gravel, silt, and therefore these shallow systems were deemed to be not appropriate for an aquifer-based system. We didn't think we could get enough water out of them. And we chose to install the monitoring well at a depth of about 121 meters below grade. And we were able to develop that 2.5-inch well at about 40 gallons a minute or 2.5 liters a second. With a fairly successful test well, although deep, we thought we should proceed further with an actual pump test. And therefore we went in with a water well contractor about 100 meters north of that detailed core hole and drilled down to about the same depth to the bedrock interface and found mostly similar stratigraphy, but unfortunately a little finer than in the cored borehole. And as you know, it doesn't take much of a change in grain size to drive your Ks much lower. We did install a 6 5/8 standard water well casing and a screen about 112.5 to 121.5 meters below grade. And then we proceeded with a step test. We started at 3.2 liters a second and then ramped it up a little while later to 6.3 liters per second. Those two correspond to 50 and 100 US gallons a minute. What we found, unfortunately, although the 3.2 liters per second was sustainable, the 6.3 certainly wasn't. We also noticed drawdowns of 0.5 meter and 1 meter during the two steps in that initial cored monitoring well, and demonstrating we're still in the same aquifer with decent connection. This is a detailed plot of the drawdown test that was performed, the step test. And you can see, obviously in this case, 3.2 liters a sec, or 6.3 liters per second, or 100 gallons a minute is not sustainable. We had 70 meters of drawdown, which when you have a 90 meter borehole and a 20 meter depth to water, means you have a dry hole. However, at 50 gallons a minute, we were able to demonstrate reasonably sustainable drawdown, at least in the short term, in the order of 30 meters. So what did we learn from all this? Well, first of all, more time needs to be allotted for field programs. We all tend to spend a lot of time on the financial end and planning and everything else, and sometimes the field work gets squeezed somewhat. And in this case, we were starting to very much run out of time when it came to deciding what type of system might work best in this location. We also learned that even though we spent a lot of time with the Oak Ridges Marine Groundwater Team and others, City of Toronto, looking at locations of buried bedrock valleys in Toronto, there is still some uncertainty because these are located a fair distance below grade, and a lot of wells simply don't penetrate that deep. And Also, as we've seen from other sites, the stratigraphy of buried valleys can be quite complex and vary over short distances. So while we found relatively good supply in one area of the site, even though the site is not very large, where we put the test well was just a little bit finer and a lot less production in terms of capacity. And we did confirm that there is a deep aquifer that's present across the site, but that fine-grained nature of it may preclude it from being useful for an aquifer-based thermal energy system. And overall, the open loop solution may simply not be possible in this location. What are our next steps? We plan to do some downhole geophysics on the test well and on the cord hole, and also a seismic line, ideally along Shoreham Drive for 2020-2021, to better outline where this valley is so we can understand its topography somewhat better. And we're seriously looking to revert back to a closed loop system and either target the rock with fewer, deeper boreholes, or accept a lower thermal transmissivity in the soil and go with more shallow holes in the overburden. Overall, we believe that the potential financial reward of an open loop system may not be worth the risk. And with that, I'll stop for questions. Thank you very much for your time today.